This hands-on activity is an exploration of forces in equilibrium. We begin with just two forces and gradually increase to many forces. When forces are in equilibrium, their resultant force is zero, so we have a system which is either stationary or moving with constant velocity. We will consider only stationary equilibrium here. There are three experiments to do in this activity, and they can be done separately or all together. In the first activity, we will make a scale to measure the weight of things using rubber bands. You will need rubber bands of the same type: string, scissors, a ruler, two bottles, one full of water and one empty, and a place to store the water we don't need, like a bucket. Link the rubber bands 4 at a time to make a chain with about 8 to 10 links. Finishing with a piece of string at each end. We begin the activity by hanging the full bottle of water on the rubber bands and measuring the length of the rubber bands from where they join the string at one end to where they join the string at the other end. We will call this L1, and it is 38 centimeters. The weight of the water in the bottle is just the mass of the water in the bottle multiplied by g, which we can take as 10 meters per second squared. Then we pour half of the water from the full bottle into the empty bottle. And do the experiment again. Now the distance is 31.5 centimeters, which we will call L a half. Now the weight of the water is half that before. We repeat the measurements each time, taking out half of the remaining water until there is only 1/16 of the original water left. Now plot a graph of the length of the rubber band as a function of the mass of the water. Newton's first law says that if there is no acceleration, the total force acting must be zero. In the rubber band balance, we have just two forces: the tension in the rubber bands pulling up and the weight of the water pulling down. And these two forces must be equal and in opposite directions. From the graph we can see if the rubber bands stretch the same amount when we increase the weight by the same amount. If they do, we can say that the rubber bands are linear and the graph will be a straight line. This is good for making a machine to measure the weight of something. Now we can move on from just two forces in equilibrium to more than two. We will use rubber bands and a ring or washer for the activity. We now know that the stretching of the rubber band depends on the tension force in it. So if we see a rubber band fully stretched, we know that it has a large tension. We begin by connecting two rubber bands to a washer or a ring and pull these two bands in opposite directions. What can we say about the tension in the rubber bands and the forces? What are the directions of the forces? Now add another rubber band and see what you can say about the forces in the rubber bands. When are the forces in the three rubber bands equal? Try with four forces, four rubber bands. Is there only one way we can have the same forces in each band, so the bands are the same length? Or are there many ways? What are the conditions? When we have 2, 3 or 4 forces in equilibrium, the situation changes because of the number of dimensions the system uses. With two forces in equilibrium, they must be in a straight line, and we can see from the lengths of the bands that the forces are equal. This is in one dimension. When we have three rubber bands, we notice that the bands must always be in the same plane. This is two dimensions. If we try to make the bands the same length, we find that the angles between the bands must all be equal. So the angles must be 360 degrees divided by 3, which gives 120 degrees. This is the only way that three equal forces can be in equilibrium. With four bands, we have more freedom. We can make the forces in equilibrium in many different ways, trying to find the condition for the four bands to have the same length. Here we have forces in three dimensions. The more dimensions, the more freedom. We have seen two forces together, three forces, and four forces in equilibrium. We've seen that the different number of forces use different number of dimensions and have different forms in equilibrium. Now we will see even more complex systems of forces, but they will not be forces in rubber bands. We will now explore the surface tension forces in soap films. We will need some wire to make some shapes for the soap films to form on, some pliers, and some washing up liquid. Three shapes that you should use are a ring, a cube, and a tetrahedron. You should make the sides of the cube and the tetrahedron at least 2 centimeters, and the diameter of the ring at least 2 centimeters. You can try other shapes as well. Firstly, dip the ring into the soap solution and look at the soap film. Which way do you think the forces are pulling? Think about the rubber bands that were in a plane, like the plane in the film. The soap film is pulling on the ring towards the centre of the film. The wire is strong and the soap forces are weak, but they are strong enough to pull the soap film flat. Now try the tetrahedron. Dip it into the soap solution and look at the shape of the soap films. How many flat soap films can you see? And what angles do they make with each other? What can you say about the forces in the films? If we have three soap films meeting at a point, they will pull with the same force in each, and just like the rubber bands pulling with equal force, they make angles of 120 degrees between the planes. These three forces are then in equilibrium. Before you do the experiment with the cube, try to guess what the shape of the soap film will be inside the cube. Think about the number of soap films which must be attached to the 12 pieces of wire that make up the cube. Is it what you thought? Normally you could pull the soap film so there is a square in the middle, and you have 13 films in 3 dimensions, like having 13 or more rubber bands with equal forces in each. If there is a bubble in the middle, it is more complicated because you have to consider the pressure inside the bubble, which means that there is another type of force involved in the equilibrium. In this activity, we have tried to introduce the concept of forces in equilibrium in different numbers of dimensions, starting with 2 forces in the rubber bands and leading to 12 or more in the cube supporting soap films. Your students will enjoy working with these simple experiments, and they can be extended to other numbers of rubber bands and frameworks for the soap films.